So this video is on dividing polynomials. So the very first example is straightforward. In the sense, we have 6x raised 5 plus 9x raised 4 minus 24x cubed. And we'd like to divide it by 3x cubed. So if you look at this polynomial, I could pull out an x cubed, which would give me 3x squared plus 9x minus 24. And I have a 3 in common, so I could pull that 3 out. I'd have x squared plus 3x minus 24. Clearly, I have 3x cubed as a factor of the given polynomial, and I want to divide it by let me not skip a step. So I have 6x raised 5 plus 9x raised 4 minus 24x cubed divided by 3x cubed, and I factored it and I wrote it as 3x cubed times x squared plus 3x minus 24 divided by 3x cubed. The 3x cubed would go away and we would simply have x squared plus 3x minus 24. So we would like to do a process called long division. You can look at the steps here and you can easily remember using dad, mom, sister and brother. It simply says divide, multiply, subtract and bring down. So it is best that I explain this via example. So we have example number 2. So 2x raised 4 plus 4x cubed minus 4x squared. So, and we have to divide it by 2x squared plus 1. The goal here is to look at the first term, and we have to multiply that first term by some expression so that when I subtract, and I'll show you that subtraction step, I would get rid of that term. So I look at 2x squared, I look at 12x raised 4, and I'd like to multiply 2x squared by some expression so that I get 12x raised 4. So 6x squared when multiplied by 2x squared would give us 12x raised 4. And 1 times 6x squared, we should not forget about the second term here, which is 1. So I have to multiply that 1 by 6x squared. And 1 times 6x squared is 6x squared. But I see an x cubed term here, so when I multiply, I kind of skip one term and I end up getting 6x squared. So I'm going to skip one term and plus 6x squared. Now we have to subtract. This is where the subtract part comes into play. And when we subtract, those two terms would go away. And now comes the bringing down part. So 4x cubed minus 0 is 4x cubed. Negative 4x squared minus 6x squared is negative 10x squared. So the objective now is to come up with an expression up here so that when I multiply that expression by 2x squared, we always look at the leading term here. So when I multiply the expression up here by 2x squared, I must get 4x cubed. So that would be 2x, because 2x squared times 2x is 4x cubed. And 2x times 1 is 2x, and there is no x term here, so I'm going to put a 0 and then write two x. We subtract again, those two terms would go away. Negative 10x squared minus 0 is negative 10x squared, and there is no x term, so I'm going to insert a 0 up there, and 0 minus 2x is minus 2x. The next step is to multiply the expression 2x squared by something over there, so that we end up getting negative 10x squared. So we want negative 10x squared, and so if I put negative 5 here, negative 5 times 2x squared is negative 10x squared, and negative 5 plus 1 is negative 5. But I see an x term here, so I'm going to put 0, then I'd have negative 5. So when I subtract negative 10x squared minus of minus 10x squared is positive 10x squared, so those two would go away. Negative 2x plus 0 is negative 2x, and there is a 0 there. 0 minus of minus 5 is plus 5. So this is what we call the divisor. That is the quotient. And that would be the remainder. So key point to note is that we always subtract, and sometimes we might get a 0 remainder, and we will encounter problems like that in a bit. Before I mention something, I'd like to show a simple case. Let's take 19 and we'd want to divide that by 6. So 6 times 3 is 18, and if I subtract, I get 1. But six here is the divisor, 3 is the quotient, and 1 is the remainder. So I could take the number 19, which is what we call the dividend. So 19 can simply be written as 6 times 3 plus 1. In other words, it is simply the divisor multiplied by the quotient plus the remainder. So, in general, if we extend this idea over here, we have 12 x raised 4 plus 4x cubed minus 4x squared. That is our original function, polynomial function. We divided it by 2x squared plus 1, and the quotient ended up being 6x squared plus 2x minus 5, and the remainder is negative 2x plus 5. So based on what we did here, I can write the original function, which is 12x raised 4 plus 4x cubed minus 4x squared, and I could write it as the divisor, 2x squared plus 1, multiplied by the quotient, 6x squared plus 2x minus 5, plus the remainder, which is negative 2x plus 5. So what we're saying is we can write that expression as that. So these are the factors, and this particular polynomial in this example is not fully factorable because we have a non-zero remainder. So if we have a zero remainder, then the original polynomial is fully factorable, and we simply have things factored nicely. So let's just do a check to see if we did things properly. So I'm going to take the right-hand side, which is 2x squared plus 1 times 6x squared plus 2x minus 5 minus 2x plus 5. And I would like to know if I get the right-hand side back. So I'm going to FOIL, which would give me 12x raised 4 plus 4x cubed minus 10x squared plus 6x squared plus 2x minus 5. And the remainder part, which is right here, so we shouldn't forget that. So minus 2x plus 5. So those two would go away, those two would go away, and we would simply end up having 12x raised 4 plus 4x cubed, and negative 10x squared plus 6x squared is negative 4x squared. So it seems like we did it right. So now we have to divide x raised 4 minus 81 by x minus 3. I always recommend that if we are skipping multiple terms, in the sense, if you look at x raised 4 minus 81, it doesn't look like a typical polynomial function where we have x raised 4, then x cubed, then x squared, then x, and finally the constant. So in a division of this sort, it is always easier if we insert some terms. So I could write it as x raised 4 plus 0x cubed plus 0x squared plus 0x minus 81. And I'd like to divide that by x minus 3. So I have to multiply by an expression over here with x over there so that I get rid of that term. So if I multiply x by x cubed, I would get x raised 4. And negative 3 times x cubed is negative 3x cubed. And let us subtract, and those two terms would go away. 0x cubed minus 3x cubed is positive 3x cubed. The other terms, when we bring it down, we simply have 0, 0, and 0. So we'd get 0x squared plus 0x minus 81. Now we've got to multiply and get an expression here so that we get rid of 3x cubed. So if I multiply x by 3x squared, I would get 3x cubed. The next term, 3x squared minus 3, is negative 9x squared. And those are the only terms we have. And when we subtract, those two would go away. 0x squared minus 9x squared is 9x squared plus 0x minus 81. We have to come up with an expression here so that when I multiply x by that expression, I get 9x squared. So that expression would be (9x). 9x times x is 9x squared. 9x minus 3 is negative 27x. So subtract and those two would go away. We have 0x minus 27x, which is 27x, and minus 81. So plus 0 there. So we've got to multiply x by an expression here so that we get 27x. So that has to be 27. 27 times x is 27x. 27 minus 3 is negative 81. And when we subtract, they are identical terms, and I get 0 remainder. Recall from the previous problem, we have x cubed plus 3x, x raised 4 minus 81. That is the original function, and we know that we can write it as the product of the divisor and the quotient plus the remainder, and the remainder is 0. So we simply have x minus 3 times x cubed plus 3x squared plus 9x plus 27. So you can see that we took the original polynomial, which is x raised 4 minus 81, and we expressed it in that form. And if you notice, that is the first factor, and that is the second factor. And since we don't have a remainder, we successfully wrote the original function as the product of two factors. So x raised 4 minus 81 is fully factorable. If you look at the previous problem, it was not factorable. So this entire process is quite long. Perhaps that's why we call it long division. We have something called synthetic division. It typically works if you divide a polynomial by a factor that is of the form x minus c. It is very important. You can only divide it by x minus 3. For any other case, we have to use long division. There is no other way. But if we have a polynomial and if we have to divide it by x minus c, life is actually easier. So, which is what is summarized here. If you look at it, we must have an exponent of 1. The coefficient here should be 1, and it is of the form x plus 3. It is best if I explain this via example. I highly recommend that you go back and look at the process summarized here after you follow the example. So the process is quite straightforward. So we write the coefficients that we see in the original polynomial. So what we have here is 4, 7 and negative 26. And we want to divide it by x plus 4. But mind you that we can only use synthetic division if we have something of the form x minus c. But that is not the form we have here. But fret not, we could write x plus 4 as x minus of minus 4. Now this is of the form x minus c, and c is negative 4. So we take that value, negative 4, and put it over here. Now we bring down the 4 and we multiply those two and we add it up there. So negative 4 times 4 is negative 16. We multiply those two and put it over there, and then we add. This is in stark contrast when compared to long division, where we always subtract. When it comes to synthetic division, we always add. So 7 minus 16 is minus 9. Now we take that negative 4 multiply it to negative 9, put it up there, we have positive 36. We add again, and since this is the last term, we are going to box it, and when we add negative 26 to 36, we have positive 10. So we divided the original function by x plus 4, which would imply that x plus 4 is the divisor. And those two numbers would form the coefficient of the quotient. And you should always start the quotient at 1 degree less than the original polynomial. So the degree in the original polynomial is 2, so we start at x. So 4 times x, that 4 comes from that term there, and after that is a constant term, so we have negative 9 as is, and that would be the quotient. So the original polynomial 4x squared plus 7x minus 26 would equal to the divisor multiplied by the quotient plus the remainder. So the term that we see here is the remainder, and that would be 10. And here, this particular polynomial is not fully factorable because the remainder is not 0. So here we have an interesting case again, where we have x raised 4 plus 1296. And you can see we jumped from a degree of 4 to a degree of 0, x raised 0. In other words, we are missing terms in the middle. So what do? We start with the coefficient of the highest degree, which in this case is 1. And we are missing the x cubed term, so 0 for that. Missing the x squared term, 0 for that. Missing the x term, 0 for that. And the last term is the constant term. We have 1296. And it is in a nice form, x minus c, and we can use it with synthetic division. So that is c, so c goes here. We bring down 1. We multiply 6 with 1 and put it over there. And we always add. Do not forget, with long division, we always subtract. With synthetic division, we always add. So 0 plus 6 is 6. And we multiply 6 with 6, put it over there. We have 36. 0 plus 36 is 36. And six times 36 is 216. So we put it over there. 0 plus 216 is 216. And lastly, we multiply 6 by 216. We end up getting 1296. And we add those two. We have 12, 9, 6, and 2. Oh, it's 5. And we could always foil this. As I mentioned earlier, we could have x raised 4 plus 1296. That is our original function. We can write it as the divisor multiplied by the quotient plus the remainder. So the divisor here is x minus 6. X minus 6 multiplied by the quotient. Keep in mind, the original polynomial had a degree of 3. So we start with 4. So we start with 3 x cubed. The coefficient of x cubed is 1. So 1x cubed is x cubed. Then we have x squared. The coefficient of x squared is 6. The next term is x. The coefficient of x is 36. And lastly, we have 216, which is a constant term. Do not forget the remainder. The remainder is 2592. So we could always foil this back in and see if terms go away. They should cancel each other, and things should just disappear, and you can try that at home. So what we have now is x cubed plus 8x squared minus 3x minus 90. Let's write down the coefficients. X cubed has a coefficient of 1, x squared has 8, x has negative 3, and the last term is negative 90. And we are dividing it by x plus 5, which would imply x minus of minus 5. So c has to be 5. Sorry, negative 5. So negative 5 goes up there. Bring that 1 down. Negative 5 times 1 is negative 5. 8 minus 5 is 3. Negative 5 times 3 is negative 15. Put it up there. Negative 3, negative 15 is negative 18. Negative 15 times negative 18 is positive 90. And we have to add, as always, which makes that 0. So, the original polynomial is x cubed plus 8x squared minus 3x minus 90. That would equal to the divisor, which is x plus 5, multiplied by the quotient. The quotient starts at a degree less than the original degree, and strictly speaking, 1 less than the original degree. So we start with x squared. The coefficient of x squared is 1. The next term is x. The coefficient of x is 3. And the last one is simply a constant, and the remainder plus 0. So the entire term plus 0 is simply x plus 5 times x squared plus 3x minus 18. So that is factor 1. And that is an expression. And we want to know if we can factor it, because if we factor it, we can find the zeros. So this has 2 factors. And how do we find the 2 factors? Well, we can either try to factor it, or we could use the quadratic formula to factor it. So I can factor x squared plus 3x minus 18 as x plus 6 times x minus 3. So naturally we have 3 factors. That is factor 1, factor 2, and factor 3. And we set each factor equal to 0, and we solve for x to find the zeros. This would imply x plus 5 equals 0, x plus 6 equals 0, and x minus 3 equals 0. So x would equal negative 5, x would equal negative 6, and x would equal positive 3. So the 3 zeros are negative 5, negative 6, and 3. So here it is given that 1 is a 0. If we go back to the previous problem, we divide by x plus 5, and the 0 happens to be negative 5. So x plus 5 here, the 0 is negative 5. So now the 0 is positive 1, which would imply the divisor is x minus 1. So the value of c is 1. So pretty much what we're trying to say here is the value of c in synthetic division is simply the 0. So 1 goes up there. Coefficient of x cubed in the given polynomial is 1. Negative 13 for x squared, 47 for x, and negative 35 for the constant term. So bring the 1 down, we have 1. 1 times 1 would give us 1. We always add. Negative 13 plus 1 is negative 12. 1 times negative 12 is negative 12. When we add 47 and negative 12, we get 35. 1 times 35 is 35. When we add, we get 0. So the divisor is x minus 1. So we could rewrite the original polynomial as the product of the divisor and the quotient. The original function starts at degree 3, so we start at 2, so x squared, the coefficient of x squared is 1. The next term is an x term, the coefficient of that is negative 12, so negative 12, and the last term is the constant, so plus 35. The remainder is 0, so we have x minus 1 and x squared minus 12x plus 35. But note, in this problem, it clearly says we have to solve, which would imply we have to set the original function equal to 0 and solve for x. If you look at the original function, it might seem scary that finding the 0 might be an impossible task, but we rewrote that original expression in that factored form. So we can rewrite the original expression as x minus 1 times x squared minus 12x plus 35 equals 0. The second term here can be factored as x minus 7 times x minus 5. So we have factor 1, factor 2, factor 3. We set each factor equal to 0 to find the solution. Which would mean x is 1, 7, and 5. So the solutions to the equation are the zeros of the polynomial. And the polynomial in question is that. So here in example 8, we have to show that 3 is a solution of the equation. So if 3 is a solution, this would imply 3 is a 0. We sort of are going in reverse compared to the previous problem, which would imply x minus 3 equals 0, because it is a 0, and if we move negative 3 to the other side, we get that statement that 3 is a 0, which would imply that 3 is a solution. So since x minus 3 is a 0, or since 3 is a 0, x minus 3 is a factor. So we can divide the polynomial by x minus 3. If you know that a function is a factor of a polynomial, we can always divide that polynomial by that particular factor. So we have 14, negative 17, negative 16, and negative 177 corresponding to the coefficients in the original polynomial. And the value of c is simply 3. 3 goes up there. Bring that 14 down. 3 times 14 is 42. We always add negative 17 plus 42 is 25. 3 times 25 is 75, and 75 minus 16 would simply be 69. Oh, sorry, 59. And 59 times 3 is positive 177. When we add, we get 0, which would imply the original polynomial can be written as the divisor, x minus 3, times the quotient, and we always start the quotient at degree 1 less than the original polynomial. So we start at x squared. The coefficient of x squared is 14. And the next term is x, the coefficient of that is 25, and the last term is 59. The remainder is 0, so we have x minus 3 times 14x squared plus 25x plus 59. So x minus 3 is a solution, or 0, or a factor. So we have x is equal to 3, that is one solution. Certainly is a scary expression. We want to set that equal to 0 and solve for x, and we could simply use the quadratic formula. So I would make this do it yourself. Use the other two solutions can be found using the quadratic formula. So here we know that negative 2 is a 0. If negative 2 is a 0, x plus 2 is a factor. So that would mean that negative 2 is a 0, because if you set x plus 2 equals 0, you get x as minus 2, so minus 2 is a 0. So how do we solve this equation? Step 1, we divide x cubed plus 7x squared plus 4x minus 12 by x plus 2. And if we can factor it fully, in the sense if we can factor x cubed plus 7x squared plus 4x minus 12 in its entirety, fully factorable, then we can readily solve. So we are going to make use of synthetic division to see if the given polynomial is fully factorable. So the coefficient of x cubed is 1. The coefficient of x squared is 7. The coefficient of x is 4. And the last term is simply negative 12. And we have to divide it by x plus 2, but keep in mind synthetic division works only for a factor of the form x minus 2, so we write that 2 as x minus of minus 2. So that would be C. So negative 2, bring the 1 down. Negative 2 times 1 is negative 2. We always add 7 minus 2 is 5. Negative 2 times 5 is negative 10. 4 plus negative 10 is negative 6. Negative 6 times 6 is positive 12. When we add, we get 0. This would mean x cubed plus 7x squared plus 4x minus 12 would be equal to the divisor, which is x plus 2, multiplied by the quotient. The quotient always starts at a degree 1 less than the original polynomial. So we start at x squared. The coefficient of x squared is 1. So 1 times x squared is x squared. The coefficient of the x term is 5. And the constant term, which is simply negative 6. So we want to solve equals 0, but we realize that we can rewrite, or we can write that in terms of the factored form. So x plus 2 times x squared plus 5x minus 6 equals 0. These are one and the same. And we can factor x squared plus 5x minus 6 as x minus 3 times give me 1 second here. Expected the problem to go in a certain direction, but perhaps I'm using the wrong factor here. It should be x plus 6 times x minus 1 equals 0. So factor 1 would be x plus 2 x plus 6 is factor 2, and x minus 1 is factor 3. We set each factor equal to 0 and solve for x. Which would give us negative 2, negative 6, and positive 1. Therefore, the solutions to zero are simply the zeros I should say, oh, that's fine, are simply the zeros. So what are they? Those are negative 2, negative 6, and 1.